Gravity, the invisible force that binds the cosmos. It dictates the motion of celestial bodies, governs the rise and fall of tides, and anchors us to the Earth. But what exactly is gravity? Is it a force pulling objects together? Or is it something far more intricate, woven into the very fabric of space and time? For centuries, humanity has sought to understand this fundamental phenomenon, crafting theories that refine our perception of the universe. In this documentary, we embark on a journey through the evolution of gravitational theory, first through the classical insights of Sir Isaac Newton, then through the revolutionary ideas of Albert Einstein. Finally, we will explore how these theories compare, evaluating which might be closer to the true nature of reality. Along the way, we will examine the perspectives of today's leading physicists as they strive to unravel gravity's deepest mysteries. Newton's gravity, a universal force. Our story begins in the 17th century when an English mathematician and physicist, Sir Isaac Newton, laid the groundwork for classical mechanics. His laws of motion and universal gravitation provided an unprecedented mathematical framework for understanding the physical world. Newton's law of universal gravitation states that every mass in the universe attracts every other mass, with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton's insights allowed scientists to predict planetary motions with remarkable precision. His framework explained Kepler's laws of planetary motion and provided the foundation for classical physics. More than just a mathematical breakthrough, Newton's work laid the groundwork for practical applications, from predicting eclipses to calculating the trajectories of cannonballs. Yet, Newton himself acknowledged a fundamental mystery. What was the true nature of this gravitational force? He described it as an action at a distance, meaning objects could exert forces on each other even without physical contact. But how could this be possible? The concept was unsettling even to Newton, who famously wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. For over 2 centuries, Newton's theory remained unchallenged. But scientific progress often comes with anomalies, small discrepancies that hint at deeper truths waiting to be uncovered. Einstein's gravity, the fabric of space-time. Fast forward to the early 20th century. The Newtonian model had successfully explained many aspects of the physical world, but certain anomalies, such as the unexplained precession of Mercury's orbit, hinted at its limitations. Enter Albert Einstein. In 1915, Einstein unveiled his general theory of relativity, fundamentally redefining our understanding of gravity. Rather than being a force acting at a distance, Einstein proposed that gravity arises from the curvature of space-time itself. At the heart of Einstein's theory is the idea that massive objects cause space-time to curve, and this curvature dictates the motion of objects. This is mathematically represented in the Einstein field equations. Einstein's equations tell us that mass tells space-time how to curve, and curved space-time tells objects how to move. One of the most striking predictions of general relativity is the bending of light by gravity. In 1919, during a solar eclipse, Arthur Eddington's observations confirmed that light from distant stars bent around the sun precisely as Einstein's theory predicted. This was one of the first major experimental confirmations of relativity, catapulting Einstein to worldwide fame. Further predictions included gravitational time dilation, black holes, and gravitational waves, all of which have since been verified by observation and experiment. Unlike Newton's instantaneous force, general relativity offered a deeper geometric understanding of gravity, fundamentally altering our perception of reality. Which theory is closer to reality? Newton's laws remain incredibly useful, particularly in everyday applications. Engineers, astronomers, and physicists still rely on Newtonian mechanics for calculating rocket trajectories and planetary orbits, where relativistic effects are negligible. However, general relativity is necessary in extreme conditions, such as near massive celestial bodies at high velocities, or when dealing with the large-scale structure of the universe. GPS satellites, for example, must account for both special and general relativity to function accurately. Yet, even Einstein's theory is incomplete. General relativity does not integrate seamlessly with quantum mechanics. the framework that governs the microscopic realm. The quest for a theory of quantum gravity, a unification of general relativity with quantum mechanics, remains one of the most significant challenges in modern physics. The future of gravity: insights from modern science. Today, physicists are actively searching for a deeper understanding of gravity. Several approaches are being explored to reconcile general relativity with quantum mechanics. One leading contender is string theory, which proposes that fundamental particles are not point-like but rather tiny vibrating strings. In this framework, gravity emerges naturally from the vibrations of these strings. String theory also predicts extra dimensions beyond the familiar four of space-time. Another approach is loop quantum gravity, which suggests that space-time itself has a discrete quantized structure at the smallest scales. This theory challenges the classical notion of smooth space-time and attempts to bridge the gap between quantum mechanics and gravity. Experimental efforts are also underway. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, aims to detect gravitational waves with unprecedented precision. Additionally, studies of black holes, neutron stars, and the early universe continue to provide insights into the nature of gravity. Some physicists, like Eric Verlinde, propose that gravity is not a fundamental force at all, but rather an emergent phenomenon arising from underlying quantum processes. These ideas challenge conventional thinking and may lead to a paradigm shift in our understanding of the cosmos. Ultimately, the future of gravitational research remains an open frontier. Whether through unification theories, new observational techniques, or entirely novel concepts, the quest to fully understand gravity continues to push the boundaries of human knowledge. From Newton's classical laws to Einstein's elegant curvature of space-time, our understanding of gravity has evolved dramatically. Yet, questions remain. Could a new theory, perhaps involving quantum gravity, string theory, or modifications to general relativity, unlock deeper truths? The pursuit of gravitational knowledge continues, driven by a desire to understand the very fabric of reality. Whether through the observation of black holes, gravitational wave astronomy, or breakthroughs in theoretical physics, the next revolution in our understanding of gravity may be just beyond the horizon. Stay tuned, as the cosmos still holds many secrets waiting to be uncovered. Subscribe for more cosmic facts.